All right, I'm back. We're kind of in the middle of page 310. We've been working on this problem. So f of x is the absolute value of x squared minus 16 plus 2. And we created a graph, and then we basically use the graph to identify the critical points. So there were two where the derivative doesn't exist, and there was one where the derivative is equal to 0. So let's see if we can answer the rest of this. So we want to write f of x as a piecewise defined function. All right, so there's an absolute value involved, and that's kind of like the key thing here, right? So the absolute value of x squared minus 16 is x squared minus 16 anytime x squared minus 16 was already positive. So if you look at the graph, we can see two times where that already had happened, right? So here and then here. So those are the places where we didn't need to reflect because it was already positive. So let's start. And then we needed to reflect when when x squared minus 16 was negative. So like, let me just highlight the other part. So we had to reflect on this part. So should I try to write it in those colors? I don't even know what colors those are. All right, here we go. Piecewise function. So f of x, nope, should use black for that, I guess. So f of x is, it's going to be 3 branches here. Okay, so it's going to be quantity x squared minus 16 and then plus 2. And that's true when x is, I'm going to say less than or equal to negative 4, right? So when x is less than or equal to negative 4. Where's the other branch? Well, the other branch is when x is greater than or equal to 4. So let's do that one at the same time. X squared minus 16 plus 2 when x is greater than or equal to 4. And then what is happening in between? Well, in between, because x squared minus 16 by itself is negative, the absolute value is the opposite of that. So it's negative quantity x squared minus 16. I think it's probably better though if, let me see, can I figure out what color that is? Yeah, okay. I think it's probably better to write 16 minus x squared. So I'm going to do that. But it's just, so 16 minus x squared and then plus 2 between negative 4 and 4. And so this part is actually the opposite of x squared minus 16. So that's why I wrote it that way. I think it's just a little cleaner. But anyway, this is our piecewise function. So now what we want to do in part D, we're going to write f prime as a piecewise function. Okay, so we got to be careful, but I think we can do it. So f prime of x is, okay, so for the first part here, what's the derivative of x squared minus 14? Because that's basically what this function is. So it's going to be 2x and then plus 0. So 2x. But where does that apply? It doesn't apply at negative 4 because we know that at negative 4, f prime doesn't exist. It's a sharp turn on the graph. The slope from the left is negative, the slope from the right immediately positive. There's no smooth transition. So we can't include negative 4. So that'll be when x is less than negative 4. Now in the middle, what's the slope? In the middle, the slope is just negative 2x, right? So we get 18 minus x squared. So that'll be negative 2x. And then that also doesn't apply at negative 4 or at 4. So this is kind of a big deal. When you're finding the derivative of a piecewise function, what you usually do is you just disregard all the equal to parts, and then you go back and you figure out, am I allowed to do it? Like, could I have put them? So this by symmetry will just be 2x again. And that'll be when x is greater than 4. Okay, so look at this. So I'm going to look at the limit as x approaches negative 4 from the left of f prime. So negative 4 from the left, numbers that are less than negative 4, so I should use 2x. So that's going to give me -8. The limit as x approaches -4 from the right of f of x, right? So numbers bigger than -4, like -3, whatever, I'm supposed to do -2 times -4 is +8. This is why f prime of -4 doesn't exist. And we could do the same thing at +4, but like, it's going to be the same argument. But that's why we're not allowed to put equality there. If we had gotten the same value, we could go back and fill in the equality, but in this case, we know that we're not going to, so we don't do it. So that's like a big idea. Think about it a little bit, but the key thing is, so where should I write this? Let's see. I'm gonna write it in, I only have like a couple colors that it turns out I really like using. When finding f prime for piecewise for a piecewise function. Too much going on. That's like 3,000 little dots. For a piecewise function, drop equality, check. And then sometimes you can add it back in, but most of the time you can't. Piecewise functions just tend not to be differentiable at the breaking points. And then there's all these fun questions you can answer where you force a function to be continuous and differentiable, right? Because if it's not continuous at a point, it can't be differentiable at a point. But if it's differentiable at a point, it's definitely continuous at that point. I think I said that right. I don't know. I'm pretty sure. I don't know. Roll back the tape and see if I said that right. And if I didn't, comment. So let's do the next one. Find the critical points, which are just the x values. Can't stress that enough. Which are just the x values of f of x equals 2x squared over x plus 2. Graph a function in an appropriate view window on your calculator. Okay, so we can do this. So I see a quotient, so I will be using the quotient rule. So f prime of x is bottom, derivative of the top, minus top, derivative of the bottom, all over the bottom squared. All right, we got to simplify this because if we're going to need the zeros. So what could we do? We could take out a 2x. I'm actually going to do that. I can take a 2x out of everything in the numerator. That'll leave me with x plus 2 and then minus x. It's kind of clever. I don't know if I've ever done this problem that way before. It's like, I mean, I'm saying it's kind of clever. Like, good job, me. I just never thought of it that way before. So equals getting 4x over the quantity x plus 2 squared. Okay, so what are the critical points? What's the definition of a critical point? Point in the domain at which the derivative is 0 or undefined. Okay, so if you're not thinking about it, you would say that critical point is x equals 0 because f prime of 0 equals 0. Okay, is x equals -2 a critical point? It could be, but we know that it's not because x equals -2 is not in the domain. So I'm going to address that because I think it's important. I'm going to say x equals -2 is not a critical point because x equals -2 is not in the domain. If it had been in the domain of the function, then I guess I should say in the domain of f of x. If it had been in the domain of the function, it would have been a critical point because f prime doesn't exist there. But it wasn't in the domain of the function, so it's not even an option for it to be a critical point. So the only critical point is at x equals 0. However, if I were going to do a sign chart for this thing, which I'm going to, I do want to put -2 on my sign chart because weird things can happen there. So this will be for f prime. So I'm going to put -2, not because it's a critical point, but because it's a discontinuity. Discontinuities, weird stuff can happen, so you put those. And then x equals 0. And then we test in our derivative, right? So we're going to test here, or here. So we're testing here. So -1 billion gives me a negative, and then I'm squaring in the denominator, so it's always going to be a positive in the denominator. So that's -1 So negative 1, let's say, gives me a negative, so negative. So still decreasing. And then positive is just going to give me a positive. So like, what do I think this function looks like? Well, I'm just kind of making this up because I don't really care how accurate I go at this point. I know there's a vertical asymptote. I know there's a vertical asymptote there. And then what's happening? So the function decreases everywhere. It decreases as it approaches it. So decreasing, or I could go back to f of x and do like a number line for that, which would also be useful. So decreasing, I think it's going to go like this. Decreases after that also. So I think it's going to go like this. And then at 0, you're going to have this. And then you're going to go like this. So do I think that's right? I think that's right, except I think that it should have a slant asymptote. Like I know it should have a slant asymptote, which makes me feel like it should have another 0. That the derivative should have another 0, but I don't know. I'm just like not. How can I always decrease and have that as my slant asymptote? I think I'm missing something. Let's go to the calculator. Maybe I'm not. Maybe I'm just like over and or under thinking this. Let's see. So calculator, I'm going to define f of x to be 2x squared over x plus 2. All right, let's find the derivative of this. So derivative with respect to x of f of x. Ooh, what the heck? Let me go back and see if I can fix this. This is another one of those things. So you see how like, because I decided to try to extend it, I suddenly was like, I have made a mistake. Also, I was kind of like lauding myself for doing this in a different way. Maybe I just like am totally wrong on this. All right, well, can we find the problem? Bottom, derivative of the top. I got the derivative of the top wrong. You were probably yelling that for like 10 minutes. All right, what can I do? This has got to go because it's not right. So I'm gonna get rid of that. Let's cut you. You're gone. This has got to go. I'm gonna cut you. Cut. Okay. Let's do it. I'm hoping that part of my description still works, so I didn't cut that. Here we go. All right, so bottom. Derivative of the top is 4x. Wait, maybe? Did I maybe have that right? I don't even know. Minus bottom derivative of the top minus top, which is x plus 2. Derivative of the bottom, what? The top is not x plus 2. Bottom derivative of the top minus top, 2x squared. Derivative of the bottom is 1 all over the bottom squared. Okay, so I don't know. F prime of x is, I'm just going to expand it because I'm afraid I'm going to mess this up again. So it's going to be 4x squared plus 8x minus 2x squared over x plus 2 squared. Woo, okay. So I like sort of apologize, but sometimes I think it's good for people to see me making these mistakes because, you know, everybody does it. But if you overthink your problem, you might realize what your mistake was. So f prime of x is, now I take out a 2x and I'm left with an x plus 4 and then over x plus 2 squared. I'm just going to sneak a peek at the calculator and see if that's what I got. That is what I got. Okay, so now we're good. All right, x equals 0, still a critical point. X equals, I can just squeeze it in. X equals -4 is critical point because f prime of -4 equals 0. Okay, I'm going to do the sign chart again because, like, why not, right? So here we go. F prime -4, -4, -2, and 0. Okay, here we go. Negative a billion gives, remember, we're going back to the derivative here, which is now correct. Okay, negative a billion gives me a negative, so positive. That's what I was missing last time. I was like, how is this possible? That's a first degree factor, so it's going to have a sign change there. This is a second degree factor of the denominator, but it just means you're not going to have a sign change there. So this is still negative. And then a billion gives you a positive. Okay, so what might this look like? You're still going to have this. And then you're going to end up with like a relative maximum at -4. So let me like make that happen. And then decrease. I tried. Then you're going to get a relative minimum here. So you're going to kind of go like this. It's going to look something like that. This is a really rough sketch as to what f of x might look like. I do think it's going to have a slant asymptote. So let me go back to the calculator and obviously finish this off. So let's see. Let's graph f of x. Now we know that -4 and 0 are both really important. We think that there's actually a relative maximum at -4. So I'm going to zoom out. Look at that. So this is one of those ways in which calculus is very helpful when you're drawing graphs, because it tells you where to look, right? So I think that the maximum that I'm seeing is definitely at x equals -4. And there it is. And I think that this minimum that I'm seeing is definitely at x equals 0. And I know that there's a vertical asymptote at x equals -2. I also think there's a slant asymptote. Let's go back here. And you can find slant asymptotes by using expand, which is menu, option 3 for algebra, option 3, and then expand f of x. And I get this. The slant asymptote, you disregard the remainder, so 8 over x plus 2, gone. 2x minus 4. Let me add that to my graph. So tab 2x minus 4. There's your slant asymptote. It looks basically like I thought it was going to, and I knew most of it because of the critical points and where the function should be increasing and decreasing. Lord knows how long this video is. So I'm going to wrap it up here, and I'll obviously be back to keep going. So hopefully the next one goes a little bit better, but I will see you there, and we'll find out together.